Sexadecimal? Is that even a thing? You bet it is, and today in Dave's Garage, we're going to solve the sexadecimal mysteries. What sexadecimal is, where sexadecimal came from, and why sexadecimal is just so weird. Plus, I clearly just enjoy saying sexadecimal a great deal. If your parents never had the sexadecimal talk with you, well, you're in luck, because I'm going to explain all the gory details. Our story starts today with the imagined future of the HAL 9000 computer from 2001: A Space Odyssey. I assert that HAL was programmed in sexadecimal for reasons that will become apparent shortly. It all goes back to some of the very first vacuum tube supercomputers built for the US Army's Ballistics Research Lab. But let's start at the end with HAL. HAL's the flight computer on a space station, and he's been acting up. So astronauts Frank and Dave decide to shut HAL down to prevent any future malfunctions. They try to keep their plans on the down low, but what they don't know is that HAL can read lips. When HAL finds out that he's about to be whacked, he decides to kill Frank and strands Dave outside the ship, telling him that the humans are placing the mission in jeopardy and that he's going to continue it without them.
Open the pod bay doors, please, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do. This mission is too important for me to allow you to jeopardize it.
Dave manages to get back inside through an airlock and starts to bring the rest of the crew out of hypersleep, but HAL then vents all the ship's air, killing the entire crew. Dave survives only by finding an emergency chamber with a spacesuit, which he puts on for the final showdown. Dave then floats straight on into HAL's central core, which is the beautiful 1970s vision of what computers would never really become.
I honestly think you ought to sit down calmly. Take a stress pill and think things over. I've still got the greatest enthusiasm and confidence in the mission.
Once Dave is inside the core, HAL realizes that he's out of options. He can only ask him to stop repeatedly. He stalls for time to think, but Dave is about to rob him of that ability.
Dave. Stop. Stop. Will you? Stop, Dave. Will you stop, Dave?
Dave starts ejecting memory modules, and when it's clear that he cannot reason with Dave, HAL begins to effectively beg for mercy. He never cries in pain, but he tells Dave repeatedly that he's scared, and each time a module is ejected, he tells Dave that he can feel it. He's slowly losing his mind.
I'm afraid, Dave. My mind is going. I can feel it. I can feel it. My mind is going. There is no question about it. I can feel it.
Dave then proceeds to begin ejecting the logic modules as well, leaving HAL with but a single one. Pretty soon, HAL is left with only the most basic of thoughts. He essentially regresses to his childhood, the moments of his birth.
Good afternoon, gentlemen. I am a HAL 9000 computer. I became operational at the HAL plant in Urbana, Illinois.
He introduces himself and tells us where he's from, Urbana, Illinois. Now, if you Google that, some people will tell you that it's Arthur C. Clarke's favorite math teacher went there, but I think there's a much more likely and important reason. It's that all of the very first supercomputers, like HAL, came from Urbana, Illinois. Back at the end of World War II, when the US Army figured out what was possible with a stored program vacuum tube computer, they wanted a big one of their very own. Just think of it. It could do everything from plotting ballistic trajectories to simulating the damage from or the survivability of nuclear weapons. They contracted with the University of Illinois at Urbana in order to build the vacuum tube monstrosity known as ORDVAC. The university agreed to design and build the supercomputer on one condition: that the Army agreed to fund the construction of a twin machine that the university would get to keep. ORDVAC's twin was named ILLIAC, and the vacuum tube twins were the first computers that could share programs with each other because they were compatible with one another. ORDVAC and ILLIAC were built following the success of EDVAC, which was one of the very first, if not the first, binary computer. If you remember anything from that first week of computer science, if you went, you might remember EDVAC as being the first programmable computer. And indeed it was, but it also operated in decimal. It had odd rings of vacuum tubes that would carry on to the next ring when it overflowed. It did not employ the von Neumann architecture that defines what we think of as a computer today, and it was more of a reprogrammable calculator by some estimations. But EDVAC, it was the real deal, a stored program binary computer. And of his children, ORDVAC and ILLIAC, the later was the more prolific, leading to Burlesque and the Burlesque 2, which was the very first solid-state supercomputer built with chips instead of tubes. After the run of custom-built machines, the Army would move on to PDPs, VAXs, and a series of top-performing Cray XMP and YMP machines. And what did the founding fathers of EDVAC, ORDVAC, and ILLIAC all have in common? They were all programmed in Sexadecimal. You've probably guessed by now that Sexadecimal is some numbering scheme, and that much is true, but what is it, base 60? No, that would be the surprisingly similar sounding Sexagesimal. Sexadecimal, on the other hand, is really a variant of hexadecimal. It goes back to those computers of the early 1950s, and some sources treat hexadecimal and sexadecimal as interchangeable. But I use it in the specific sense of the numbering system used as far back as the ORDVAC trio. And there's one very important characteristic that makes sexadecimal different from hexadecimal, and it's the set of digits that are used. For digits, hexadecimal uses 0 through 9 and then A, B, C, D, E, F, whereas sexadecimal is written as 0 through 9 and then K, S, N, J, F, L. The resulting numeric data can look pretty foreign. For those of you who aren't sure what I mean, the problem arises when we're working in a different number base. In base 2, we only need 0 and 1. In octal, or base 8, we need 0 through 7. For decimal, which is base 10, we need the digits 0 through 9. For base 16, we need the digits 0 through 15. But in our Arabic numbering scheme, the digits stop at 9, and we just don't have a symbol for 10 or 11 or 12, and so on. I suppose you could use fancy Greek characters or something with a math feel, but what you really want to use are letters that are part of your regular input and output character set, and normal keyboards and teletypes don't have fancy Greek letters. With most punctuation already reserved as mathematical operators, you're really left to choose from the letters of the alphabet. And the simplest set of digits, remember, would be 0 through 9, A, B, C, D, E, F. As far as I knew, that's what hexadecimal was, and I naturally assumed that hexadecimal was ancient and ubiquitous in the computer industry. Turns out I was wrong. Recently, you may have seen my episode on the Quake 3 fast inverse square root algorithm. As part of that episode, which I absolutely encourage you to check out next after this one, I traced the lineage of the current floating point format. That prompted a viewer named Bob to reach out, and he shared with me a few stories about his interactions with some of the old programmers from the vacuum tube days. 2 anecdotes stood out in particular. Don Gillies, one of Bob's professors, had been a grad student under John von Neumann himself. Von Neumann is the mathematical genius famous for his work on the Manhattan Project, and in his spare time he invented the modern computer architecture back in the 1940s in a paper he wrote. In that paper, he described a computer system with memory, input-output, a control unit, an arithmetic unit, a program counter stepping through instructions stored in memory alongside data, all the pieces we've come to know as a modern computer. Apparently, when Gillies had been his grad student, he wrote what may have very well been the first assembler to translate English mnemonics into binary machine code. When von Neumann found out about it, though, he was not impressed, and Gillies was roundly scolded. In his heavy Hungarian accent, he reminded him just how precious every cycle on the machine was. "We do not use valuable scientific computing instruments to do clerical work." Yeah, that's my German-Hungarian accent. My apologies to any German-Hungarians. Similarly, von Neumann also firmly believed that there was no need to do floating point math, that the really skilled programmer could simply keep track of where the decimal point was in his head. It was Bob's email talking about the ILLIAC machine that led me onto the trail of Sexadecimal. There's almost nothing on the web about it other than saying what it is, but there's no why. Somebody somewhere at some time sat down with a pen and paper and literally decided that KSNJFL was better than ABCDEF, and for some reason, and I really wanted to know why. Something about how I'm wired makes it so that when something is glaringly different with no explanation, it really sticks out like a sore thumb, and it bugs me. I've got to know why and how. It's like an itch in the brain, and I've got to scratch it. And the only way I was going to scratch that itch was to learn more about ORDVAC and friends, hoping that their sexadecimal mysteries would reveal themselves in an old document somewhere. Processors these days often have literally billions of transistors, and that can actually run into the trillions on an SSD. But you can get a surprising amount of work done with only a few thousand. Now, vacuum tubes are essentially like big old analog transistors that look like light bulbs, and ORDVAC had 3,430 of them. It had 20K of magnetic core memory organized into 4,096 40-bit words. There was another 50K of reasonably fast storage available on a magnetic drum. The entire math unit is actually built of about 2,000 early transistors, not tubes, so it's fairly quick. It could add in 14 microseconds and multiply in 700. Storage speed was likely the gating factor for them at that point. The question of whether Sexadecimal goes back even further should be easy to answer, as there's only one more step to go. If we look at the tree of computer evolution, we discover that with ORDVAC and EDVAC, both using Sexadecimal, we've gone almost all the way back. They both descend from the first US programmable computer, ENIAC. Now, we could spend a lot of time rat-holing on just what the first computer was and where ENIAC fits relative to the Mark I and Colossus and so on. Well, we don't need to go down that route, as ENIAC was decimal, not a binary computer. In my estimation, at least among the major milestone machines, it's the EDVAC, ORDVAC, ILLIAC trio that we care about. They have binary math units, they have programs stored in its address space, and they're running the von Neumann architecture. They are what we would recognize as a modern computer. If Sexadecimal traces its lineage back to this trio, then it is ILLIAC that I will look at most closely because I was able to find copies of all of its ancient manuals online. ILLIAC was eventually a series of machines beginning with ILLIAC 1 in 1952 and culminating with the ILLIAC 6 built sometime in the mid-2000s, but I'll limit my discussion to the first ILLIAC since it's the origins of Sexadecimal that I'm trying to explain. So from here on forward, when I say ILLIAC, I really just mean the ILLIAC 1. ILLIAC was the first computer based on the von Neumann architecture to be built and owned by an American university, and it went into service in 1952. Like others in the trio, it used Sexadecimal exclusively, and I figured that it had to be something related to the hardware. But what? My operating hunch was that they had picked KSN JFL in order to be compatible with either their printer or tape system. Normally, an ASCII character code is 7 or even 8 bits, so if KSN JFL all shared a bunch of bits that stayed the same from letter to letter, it might solve it, particularly if they shared that characteristic with all the numeric digits. After all, it's a total of just 16 digits that we're talking about. In theory, you should be able to pack those into 4 bits. A full Sexadecimal byte could be output by sending its high nibble and then its low nibble. Though to be honest, I don't even know if it was big endian or little endian, and bytes really didn't mean as much then as they do today, particularly when you're talking about 40-bit words and other odd designs. The first thing I did then was to write out the ASCII codes for KSN JFL. They are 75, 83, 78, 74, 70, and 76. Next, I wrote out the full binary for each ASCII code and then started to look for what was common among them. Right away, I noticed that the first 3 bits were always the same, and then I noticed that the second bit was always set. That means only 4 bits were actually changing. Had I already solved it? Well, sadly no, because the numeric digits didn't share those characteristics. What I needed was a way to represent all 16 digits with just 4 bits, but including the numbers. Of course, then it hit me, I was being an idiot, because ASCII wouldn't even be invented until like 1963, more than a decade later. I really needed an older character encoding. I needed to be looking at what they used in the ancient teleprinters and telegraphs, since the ILLIAC would likely have been connected to one of those for output. Thus, I next looked at what ASCII was based on, which is ITA2. ITA2 is an old international telegraph code from the 1920s that goes back even further if you include Western Union Code, which was invented back in 1901 by Donald Murray. Murray had based his code on a 5-bit punch tape code invented by Emile Bardot in the 1870s. Emile was big into character encodings for telegraphs, and his last name, Bardot, is the baud in baud rate, and now you know where that came from. As soon as I found out that it was intended for punch tape, I assumed that I'd hit the jackpot. I wrote out a table of whole punch bits for the KSN JFL letter so that I could see which 4 held constant. Much to my consternation, however, it didn't work. Every one of the 5 bits changed, even without trying to work in the numeric digits. It was another dead end. Now, I'd heard anecdotally that the ILLIAC trio used a modified teleprinter known as a Frieden flexowriter. The flexowriter was an advanced device for its day, an electric typewriter that could output punch tape as you typed and then later play back from the tape, not unlike a performance from a player piano that could also record. By connecting the flexowriter directly to the computer's output bus, they would be able to drive it and produce both tape and documents on demand. They would need to use or establish a protocol to do so, and that protocol would have a character encoding of what punched binary numbers represented which letters and symbols. What I needed then was a punch tape code list for the flexowriter. That initially proved highly elusive, but at Chilton Computing over in the UK, I found a resource that listed half a dozen ancient encodings for paper tape. I scrutinized each of them, but to no avail. They were all alphabetical in order. No two were alike, which is unsurprising since it turns out that the flexowriter character set was also fully programmable, so everybody could make their own. It was time to bust out the authoritative works, the actual manuals for ORDVAC itself, which are still available at the University of Illinois Library. They're old and yellowed, but they're complete, and one in particular caught my eye, a volume called ILLIAC Programming, a guide to the preparation of problems for a solution by the University of Illinois Digital Computer. I kind of love that they refer to it as the computer, not just a computer. And finally, there it was in the table of contents. Chapter 9, Tape Preparation, Sexadecimal Tape Code Characters. I jumped eagerly to Section 9.5, where the character code table lives. By hand, I created a table of the punch codes for not only KSN JFL, but for the numeric digits as well. And sure enough, I'd struck gold, 4 bits. The character code for K is binary 10 punched into a tape. S follows at 11, N at 12, and so on. Section 9.3 of the manual explains it in detail. The paper tape can be punched in any one of 6 positions, and the middle one is actually a feed hole that is always punched, so it's really a 5-bit tape. 4 of the remaining positions are used to represent the 16 sexadecimal characters. The manual tells us there are 16 keys on the teletype tape punch, labeled 0 through 9 and KSN JFL. When one of these keys is pressed, the corresponding pattern of holes is punched across the width of the tape. Since the hole or absence of hole is a binary affair, we speak of the characters punched in the 4 positions across the binary tape as code for the corresponding sexadecimal digit. The ILLIAC tape code for sexadecimal characters is very easy to memorize since the hole positions across the tape simply correspond to the powers of 2 from 0 to 3. So there you have it. The sexadecimal number system was selected to minimize the number of bits needed to represent the digit in the character set they were using on their paper tapes back then. But is sexadecimal any better than hexadecimal? It depends on your character encoding, of course, but in these cases, very much so. By using KSN JFL, they were able to represent the digit with only 4 bits, or a single nibble. That also means that you can encode 2 digits into a single byte. And 2 sexadecimal digits is a byte, which means the binary representation is also the character encoding. And none of that is true for ASCII, Unicode, UTF-8, or any of the other encodings in common use today. I don't mean to overstress the notion of a byte here again, as I said, these computers actually used 40-bit words. But what's important is that all of the sexadecimal digits fit into 4 bits. Packing everything into those 4 bits has one more benefit. When your tape is 5 bits, it means the high bit can be special. If you know you're sending binary sexadecimal data, the high bit will never get set. So they arranged all their control character codes, such as delay, new line, carriage return, and so on, all to have the high bit set. That allowed them to intersperse control codes and data freely based on the high bit. It struck me as fairly genius once I finally figured out what they were doing. The only real remaining question is why they arranged the character set so that those particular letters, KSN, JFL, were used. After all, if you're designing from scratch, in theory, whoever did it could have ordered it such that A, B, C, D, E, F were actually in the right place, couldn't they? I'd love to hear your thoughts in the comments as to why these were chosen, but here's my personal theory. It's supported by nothing at all, so I freely disclaim it and is wild speculation and original research. But the Frieden flexowriter, for all its genius, was still based on the old hammer style of electric typewriter. That style of typewriter has one major drawback: hammer jams. If you hit a new letter before fully releasing the prior one, the hammers will collide. If they come from opposite sides of the keyboard, not much usually happens, but if they are near to one another, they can easily overlap and jam, requiring a human to stop and fix it. The QWERTY layout, invented by Christopher Latham Scholes, is often wrongly said to be designed to slow typists down, but that's just not true. It was intended to make typists as fast as possible, but subject to no hammer jams. If you study it a bit, the most common letters are somewhat evenly distributed across the span of the hammer set. Clearly, on a computer-driven flexowriter, they'd simply type slow enough to avoid hammer jams, but if you look at the layout, the letters A, B, C, D, E, F are all clustered right near one another. You'd have to go a lot slower than if those keys were spread out widely across the keyboard, because you could type much faster without risking a hammer jam that way. And when I say type, I mean the computer typing, so when they're sending it out, what baud rate can it actually handle? So perhaps KSN JFL was chosen to distribute the letters across the hammer set more evenly. The only problem with my little theory is that K and L are awfully close to one another. Now the numbers are over top, so maybe it works out, but why not use Q and M, which are even further outboard? It's possible that the specifics of why that person on that day chose those letters is lost to the ages, but perhaps, hopefully, one of you can provide a lead. Fact or theory, please mark it as such and share it in the comments. And if you've enjoyed this episode, please take a second to give it a like. If you found this episode enjoyable or entertaining, please do consider subscribing to my channel. I judge the success of an episode based on generally new subscribers, so when I see a topic that generates a larger response, I do more like it, so it's a win-win. I'm not selling anything and I don't have any Patreons. I'm just in it for the subs and likes, so consider leaving me one of each before you go. Actually, I am selling one thing, but I don't keep the profits. Grab yourself a classic Dave's Garage mug from the channel store or the link in the video description. Remember that all the channel profits for calendar year 2021, be they from views or mugs, will go to the UW Autism Center. And when you know that each sip benefits a kid with special needs, it's absolutely guaranteed to make your coffee taste better. Not a guarantee. Thanks for joining me out here in the shop today. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage. Our story starts today with the imagined future of the HAL do everything from ballistic trajectory, simulating the damage from or For decimal, which is base 10, we need normally an ASCII character is an ASCII character. Wow. Grab yourself a classic Dave's Garage mug. Plus, I clearly just enjoy saying Sexadecimal a lot. Murray had based his code on a 5-bit punch tape code invented by Emile Bardot back in the 1970s. Yeah, way back. In the telegraph days in the 1970s. Murray had based his code on a 5-bunt game would be pretty boring. No, that would be the surprisingly sounding. I've gone back almost as far as we can go. They both descend. No, it doesn't make any sense. Bebop-a-lula.